In this video, we're going to learn a special function called conformal mappings. Here we have another application of analytic functions that is very useful when we work with geometric aspects of a transformation. So we can talk about length, angles, and things like that. So this happens when making composition of a complex function with a path, normally a smooth path. So let's look at this theorem. This is what we call angle preserving theorem. So suppose f is analytic and we have a point A in C with the condition that at A we have a non-zero derivative. So you know that the complex derivatives are different from real derivatives. So when you say a complex derivative is zero, that means the length is zero. It can have any angle. But in real case, when we say derivative is zero, we talk about horizontal lines. But in complex, horizontal line is a non-zero situation because it has a direction. So there's a major difference between the two cases. And suppose we have two path, gamma 1 and gamma 2, a smooth path that passes through a point A. So what we have is this. So we have, we can say gamma 1, that's one path. This is gamma 2, that's another path. Those two passes at point A. And you can see that these two paths, there's an angle between the two paths. So let's call it phi, angle between the two. And then what it says that, so with an angle phi, then the f transforms gamma 1 and gamma 2 into two new pairs at fa. That means this one. Say we have these two so this is we can say gamma 1 prime, that's the image of gamma 1. This is gamma 2 prime, that's the image of gamma 2. So what it says that this angle is the same. So it's have the exact same angle phi in this situation as well. So this is the FA point. So it says that meet at FA and the transform path have the exact same angle as in the previous case. So the angle between the two paths is preserved even if you transform under the analytic function FC. So this is an interesting idea. So that's why we call this is angle preserving theorem. So it's, if the function analytic, if the derivative is not equal to 0, because if it's 0, I mean, you cannot do anything with that. If it's not 0, then what happens? The angle preserves when you transform the two paths to another to the W domain. So this is a Z domain and to the W domain. So the same angles. Okay. So in other words, what he says that analytic functions with non-zero derivative preserves angles. So we have this interesting definition. What it says that the functions that preserve angles are called conformal. So we call these are conformal mappings. Conformal mappings. The angle preserves when you transform. And theorem 3.1 says that any analytic function is conformal at the points where there's a non-zero derivative. We can look at a few cases. For example, the function 2x minus 1 is conformal everywhere because you can see that you get a non-zero derivative. Derivative is 2, which is non-zero. And if you look at z squared plus 1, which is conformal except at the origin, because at the origin you get 2z, so 2z is 0 at the origin. And then if you have hc equal 1 over z, this is a very important function that we're going to use later. is conformal for any point in the domain. So only point that is not in the domain is 0. So that means anything outside 0, it is analytic. That means you can transform all the curves conformally. So let's look at the proof of this theorem. So it's a very interesting proof. So we can assume two paths, gamma 1 and gamma 2, and you can we're going to consider the same as the parameterization. So the parameterization, the curve, we get this exact same name. Parameter of the two paths such that at t naught you get the value a. So you have two curve, and at t naught you get a. So it's a gamma 1 curve and gamma 2 curve. So you can find such a value t naught where it meets the two curves. Then you can see that gamma 1 prime t naught, you can see that's a vector because that has a direction and the length is a vector, is the tangent vector of gamma 1 at the point A, and gamma 2 prime at t naught is the tangent vector of gamma 2 at point A. Now what we do, now let's look at the images of these two. So you can find the images of gamma 1 and gamma 2 under F by the chain rule. The tangent vector of F gamma 1 at the point FA is, by the chain rule you can find, so you take the derivative and evaluate it at t naught. So you can see that by the chain rule, you take the derivative of the outside function and then put the inside function in and multiply by the derivative of the inside function. That's what the chain rule says. And if you plug in gamma 1 t naught, you get f prime a times the derivative of the inside function. And if you do the same thing with the gamma 2 function, and you can see this term is a constant. It can again appear, but it's fixed. You can do the similar calculation. So you can see, so what you get is f prime a again, because those two are equal, so it's the same value. And then gamma prime a t naught. What does that mean? This means that the two derivatives are simply multiplied by uh, the two tangent are multiplied by the same constant f prime a. So that means if you look at in the complex sense, so what will happen is, so you can see that, so that the two tangent vectors got rescaled by this value, and you can see that, and rotated by, you can say the same angle. So if you exaggerate a little bit more, let's assume you can write, because this is a complex number, you can write this one as a rho e I phi. Phi is the angle, what we normally call the argument. Then you can see that the two vectors, gamma 1 prime and gamma 2 prime, are rotated by the exact same angle phi. Because when you do in the complex calculation, what will happen when you multiply, you add an angle. So you add the angle phi every time. So that means since you add the phi, you can see that the difference is the same because you add the exact same amount to the two angles. So you can say, let's say gamma 1 prime has the angle alpha. So the new angle is alpha plus phi. If the gamma 2 prime has the angle beta, which is beta plus phi. So you can see if you take the difference, you're gonna phi gonna cancel out and you get alpha minus beta. That means you get the exact same original difference again. So that's what the theorem says. It doesn't change the difference between the two curves. So we can actually look at an example. So we have one of the very important example when we have the function f z equal 1 over z. We know that which is analytic except at the origin. So you can see that this one actually, I'm going to transform lines to circles. That we're going to discuss in the next video. So you can see, if you look at what we have is, so we have two lines, you can say L1 and L2, then transform into Z1 and C2, two circles. we can look at more details and why this happened in the next video. We actually going to do some calculations and we can see you get a if you start with the equation of a line, you end up with this equation of a circle. Now we also notice few interesting things here. So let's try to find what is the closest point in these two. So you can see if you draw the tangent line to the origin, that's how we do. So the closest point to the origin we can call it z1. Since the transform is 1 over z, what will happen? The closest point, that means it is perpendicular now, closest point actually going to map to the farthest point now. So then if from the origin, but the farthest point now is this one. So you can see if you draw, if you look across the diagonal diameter, so you have, so that's the point 1 over z1. That's across, that's the farthest point from the origin. And then same thing with the other circles. If you draw the perpendicular, so that's line 90 degree here. Now for the other circle you get this one. So you can see what is across the diameter. That is the point. So that is 1 over z. So if you call this is z2, so that's point 1 over z2. So this actually kind of give you a way to find the map of this one. What you want to do, you're going to take the 1 over value. That's going to give you the edge of the diagonal, edge of the diameter in this case, edge of the diameter. And also you can see that these two lines are crossing at perpendicular to each other. So if you call this value is a, now where is 1 over a? And you can see this is not infinity, this is a finite value. So you can see 1 over a is sitting at this point. So that's 1 over a value. That is 1 over a value. So this is 1 over a. And then also if you draw the tangent line, let's look at the tangent line. And you can see the tangent line actually cross at 90 degree. That's what the theorem says. So if the original one is at whatever angle, in this case is a 90 degree. So the new one is also at 90 degree. That's kind of very interesting. And also there are a few other things. You can see in complex, when you have these lines, we call these lines actually goes to infinity. So this is infinity. We also call the other one also infinity because there's no positive negative in this case. It's just infinity. Just go in indefinitely. And same thing for the other line as well. You can see since it's a 1 over, those infinite values actually map to the origin. So that's where they are mapping to, all those infinity. There are 4 infinities, they all map to the origin value. So that's like interesting observation here. We're gonna learn more about this in the next video with some other examples, and also we do some calculation and see like what exactly happened here. Why you get why the circles lines become circles, and you can also show that circles actually become lines in another situation. So there are like 4 cases to consider. What happened other lines, like what happened if the line passes through the origin. What happen if you have a circle which do not go through the origin. So there are 4 different cases, and we're going to discuss all those cases in the next video.